talking about today is the definite integral. By now, you've seen the area under a curve expressed like this, as a sum of rectangles. Would you guys agree with that? Does this look halfway familiar?
Yeah.
So, what does the delta x represent? The delta x in each rectangle represents the width of each rectangle. F of x sub I represented what part of each rectangle? The height. So this was height times width. Then what did the sigma mean? What did we add them all up? And then that just meant let there be an infinite number of rectangles. We will be shifting the way we write exact area down. So instead of the sigma and all the f of the x sub i's and the i's and all that stuff, we'll be instead transitioning to this notation right here. Okay. So take a look at that. And I don't know if you guys have this in your note packet. It might, no, it is not in there. So I want you guys to write principally what we have down there. So for some of you, this will be the first time that you've seen this in any meaningful way. What this is called a definite integral. And it is the last major piece of calculus notation that you will be learning about in this class. Everything else after this has to do with either integrals, of which this is, or derivatives, or links between them. So this is the last big concept. What it means, or I should start with how it's pronounced. It's pronounced the definite integral from a to b of f of x dx. Okay? F of x dx. And it is the exact same, well, not exact same, but the parts of the definite integral reflect the parts of the rectangle's some process that this came from. The dx is sort of an infinitely small width because we're dealing with like infinitely many rectangles. That's the delta x becomes sort of like a dx. F of x is the height of each infinitely small rectangle, or infinitely skinny rectangle, I should say, which is sort of exactly like f of x sub I that we had before. Now, up here we had sigma. That elongated s right there stands for sum. It actually stands for summa, which is Latin for sum, but that's what it represents. So this means add up all of the infinitely skinny rectangles from A to B, and the result is the exact area underneath f of x. Okay? You guys have any questions so far? So this is the notation that we will be using from here on out to represent the area underneath a curve, or the accumulation underneath a curve on a graph. Okay? It's not too bad. First, just to make it explicitly clear, in case it wasn't before, the sum becomes the integral sign here, which is just an elongated s. And by the way, I would recommend, it's kind of fun, that you just practice that in your handwriting just to make it look real good, because integral signs are, at least for me, one of my favorite calculus signs, and it's really cool. Once you start writing your practice problems and you look at the paper after you're done, you see integrals all over the place. It makes you feel really smart. Have you guys seen Big Bang Theory? Mm-hmm. You guys know the whiteboards in the background? Those are actual physics problems that they supposedly work on over the course of the show. And occasionally in that show and in movies and other things that have people working math, if they want the physicist or the mathematician to make it seem like the math they're working on is really high-level math, do you know what symbol they use? It's that one. They just throw a few integrals in there, and invariably people will think, oh, that's high-level math. And we're doing it. Anyway, sigma notation is that f of x goes to f of x, and then the delta x goes to dx. And I want to just reflect with you guys, in algebra, we had m. What did m mean in algebra? Slope. What was another way to say slope? Change in y over change in x. Have you guys seen that before? Now in calculus, what means slope for us? What symbol do we use to represent slope? dy dx. In both instances, do you see how the delta x in algebra becomes the dy in calculus? And the delta x became the dx in calculus as well. dy and dx mean infinitely small changes in y and x. Okay, let's take a look at the first one. Let's evaluate the integral from 0 to 2 of 4 minus 2x. All right, so what does this integral mean again? What are we using it to represent? The area underneath 4 minus 2x from 0 to 2. You guys okay with that? Now, we will not be doing these algebraically over the next couple days because we don't have the connection to do it yet. We will be doing these graphically and geometrically instead. So what I want us to do is start by drawing a graph. So talk to me about this graph. We're graphing the function 4 minus 2x. What kind of shape is it? It's a line. What's the y-intercept of this line? 4. Okay. So 1, 2, 3, 4. That's the y-intercept. And then what's the slope of this line? Negative 2. So this line actually will look like this. Now it's not just enough to graph the function. You also need to know what region you're dealing with. And what region underneath this function are we dealing with? From what to what? 0 to 2. So indicate that in your picture. Okay, we're going from 0 and we're going to 2, which happens to be that. I'm going to shade in my region. You guys will actually be able to shade. Smartboard doesn't work too well for that. And you will notice that this region is just a what? It's just a triangle. So does anyone think they can tell me what this integral is equal to? Scott? 4. You guys agree, Scott? Scott, how'd you get 4? 4 times 2 divided by 2. Okay. So this is a triangle. We can find the area of a triangle. No problem. Yeah. What if this region was 0 to 1 instead? Would it be a triangle anymore? What shape would it be? I heard it. Who said it? It would be a, yeah, if we go from 0 to 1 instead, it would be a trapezoid. And you guys know how to find a trapezoid, right? Okay. So lines, a lot of times, are related either to triangles or trapezoids. You'll be doing usually one or the other, at least the area underneath the line. Okay. Let's take a look at this integral. My, this looks fun. Anyone think they could read this out loud for me? Jack, go for it.
The integral from negative 5 to 5 square root 25 minus x squared.
I see. What's the thing at the end? dx. Because the dx is important. The dx is so important, by the way. If you forget the dx, technically your answer to the integral is infinity. Because without that dx, we're adding up an infinite amount of heights of the rectangles. And if the dx isn't there, then we're not computing area anymore, are we? Now, can you do a problem without having the dx on there and understand what it still means and have someone else do it and understand what it still means? Absolutely. But the dx is important. I don't want you to forget it. Please practice writing the dx down because it will be crucial to us when we do something called u substitution. The dx is a crucial part of each and every integral. All right, so we have the integral from -5 to 5 of the square root of 25 minus x squared dx. Now, unless someone already knows the shape to this graph, which, I don't know, maybe they do. Does anyone know what this graph looks like?
Upside down.
Not quite. That's what a square root graph looks like, but this is a little bit different. This is a circle. This is a circle with what radius? 5. So I want you guys to graph a circle with radius 5. And actually, I misspoke a little bit. This isn't a whole circle. This is only half the circle. Which half?
Top half.
This is the top half of the circle.
Looks kind of like an oval on my calculator. Is that just a window?
The reason why it looks like an oval in your calculator is because the calculator is wider, the screen is wider than it is tall, correct? There is a zoom option. If you press zoom square, I believe, that'll even out the dimensions of the window, and it should look like a circle. Okay. So then this is the area underneath this circle from -5 to 5. Okay. Now, does anyone think they can tell me what this integral is equal to then, just based off that? Pi times 12.5. How did Jack, well, how do you find the area of a normal whole circle with radius 5? What's the area of a whole circle with radius 5? That's the circumference, pi r squared. The area of a whole circle with radius 5 would be 25 pi. This isn't a whole circle though. This is how much of a circle? Half of that. So this should be 25 pi over 2, or 12 and a half times pi. What if this integral were 0 to 5 instead? Then how would our answer be different? Be half of that, or a quarter of a circle. So a -5, sorry, did I say -5 to 0 or 0 to 5? 0 to 5. Would -5 to 0 be the same as a quarter of a circle? Yeah, so 25 divided by 4 times pi, which is 6.25. Okay, mental math, Murkve. It's morning.
How did you actually solve?
How did we find it?
Yeah.
So remember, this is what shape?
Half
Half
a circle.
a circle, and we want the area of the half circle. So we're looking for, well, the area of a whole circle is the radius squared times pi. And the radius squared times pi is 25 pi. But we
How
don't,
would you do it though
with the integral,
Yeah. Without the area of the circle.
if this weren't a circle.
Yeah.
We would need another technique to do it. Right now, all of the shapes that we will be doing, you can graph and find geometrically with geometry areas. You will not encounter any graphs like parabolas yet that you don't know how to find the area geometrically in these definite intervals. Okay? They'll all be either circles or triangles or trapezoids or rectangles, things of that nature. Does that answer your question, JC? All right, next we have a few properties. So we have constant multiple property and the sum and difference property. Do these look familiar to you? Yeah. These should look like the sigma properties that we talked about a few minutes ago. The constant multiplication property for sigma notation and the sum and difference property for sigma notation. And integrals preserve those because, well, integrals are just sigmas in disguise. So we can, if we have an integral where there's just a constant inside the integral, like k or 5 or 2 or whatever, we can pull the constant outside and it goes in front of the integral. Likewise, if we have an integral of two different functions added together, like f of x plus g of x, or x squared plus x cubed, you can separate that into two separate integrals. The integral of f plus the integral of g. And it works with minus as well. And these shouldn't be too groundbreaking. They shouldn't be too difficult. It should be a natural extension of what we already know to be true about sigma notation, because it is. And if it preserves what we know to be true about sigma notation, then it should also preserve what we know to be not true about sigma notation. And I will write that down in just a second. Where is, there it is, over there. This right here, is this true? Do you think the integral of f times g is equal to the integral of f times the integral of g? No. If I'm pointing it out, actually, and with these words right on the bottom, this is almost never true, never, ever, ever, ever. Do not ever think this. Never. Do not ever, ever think that. There will always be questions like this on the AP, on my tests and or formatives, that essentially ask you, like, I'll give you two integrals and then ask, can you multiply them together? Like if one integral is equal to 5, the other integral is equal to 7, and then I might ask, is the integral times that integral equal to 35? And you're supposed to say, no, not necessarily. Okay? All right, let's take a look at a few other examples here. So the integral allows us to generalize a few things about area. A normal person might say that the definite integral is the area between the graph and the x-axis on the interval a to b, which we've already pointed out, we've already discussed. That's true, but there's slightly more to it. So on this page, could I have you guys write down the integral from a to b of f of x dx real quick, just above this little graph, or at least above the graph that's below it, because I want to be very careful about what physical meaning I assign to this for you guys. We've talked about it as area so far, but now I want to be more specific. It's not really just area under the curve. What I'd rather you guys think of it as is the accumulation under f of x. So can you please label that integral as the accumulation under f of x? Can you guys see in your mind why area and accumulation would be very much related to each other? It's like how much space is accumulated underneath the curve of the function. The reason why I'm doing this is because up until now, like area has always been positive, right? Have you ever encountered a triangle or a circle where the area was negative? I hope not. That would be a very scary thing, unless you're dealing with a circle made of antimatter, which even then, I think antimatter's properties are like the same. I don't know. Anyway, what I'm trying to say is that we will now be dealing with things that we could consider negative area, but it makes more sense to think of them as negative accumulation. So we have this little pictorial representation of what's going to go on. So if f of x is above the x-axis, it accumulates positive area. And if f of x is below the x-axis, it accumulates negative area. Yeah?
Wouldn't that happen naturally with our calculations because the height would be negative?
Exactly. So Jack asked if we were to do the infinite rectangle method on this, wouldn't that happen naturally? Because the rectangle's heights would be considered negative. And that's correct. That's why this is a negative area, actually. But it's not something that you guys have really encountered too commonly, which is why we need to point it out. So let me ask you guys this question before we go on. If you were to consider the amount of area that's accumulating as I scan from A to B, tell me what's happening to the area, whether it's increasing or decreasing as I scan. What's the area doing right here? Increasing or decreasing? Okay. Decreasing. Why do you think the area is decreasing? Because it's going backwards, it's subtracting. F of x is negative. G, what else do we know about where, when the value of it is negative, a function is decreasing? Slope. Derivatives. If a derivative is negative, then the function above it is decreasing. And right there, I wanted to point that out because there is a connection between area and derivatives. There is actually a very fundamental connection between them. All right, so let's do some problems just to type. I'm sorry, not some problems. We got to do some properties first. It'll be just 4 principal properties. We got the zero property of definite integrals. I want you to write this down. If you want, you can sketch a little picture that goes with it, but really all of these should be fairly obvious as long as you keep the picture in your head. Does it make sense why this would be equal to 0?
Yeah.
Why?
Because it's a line.
Because it's just a line. We're going from A to A. Yeah. Is this true for any function?
Yeah.
Yeah, if you start thinking about, okay, I'm going to accumulate area underneath this function. I'm going to go from 2 to 2. Are you actually accumulating any area underneath it? Nope, just from 2 to 2. No area. Okay, next one. Order of integration. What this essentially says is that if you accumulate area backwards, it is counted as negative. So the integral from b to a would be equal to negative integral from a to b. What if you had area that was below the x-axis already, but you were going backwards? What would it be counted as then? Positive or negative? Yeah. If the area was below the x-axis, but you were going backwards on it, then it would be counted as positive area, because negative negative is a positive. If we have positive area, but instead of going from 1 to 2, if we go backwards and count it from 2 back to 1, it's counted as negative area, because it's like we're de-accumulating area from it. We're subtracting. Of all these properties I'm about to go through, I think that this is maybe the trickiest one to really understand. But once you go through a few examples of it, you see it in action, it's really not too bad. All of these will be in your guys' DNA by the time we're done with this unit. So if they're confusing right now, have hope that they shouldn't be in a couple of days. We have additivity. Which says that the integral from a to b plus the integral from b to c should be equal to the integral from a to c. If you start accumulating area from one point to another point and then pick up right again from that last point, go to another one, you end up just accumulating area over a whole span. And I've got a little example down here. Integral from 1 to 1.5 of x squared dx plus the integral from 1.52 of x squared dx is just the integral from 1 to 2 of x squared dx. You guys okay with this? Does this make sense? Yeah. A lot of these should be, like I'm trying to say, should be fairly common knowledge. And the last piece is probably the least common property, but it still should make sense as we see it. It's called domination. And it basically says if f of x is greater than g of x on that interval, then the integral of f must be greater than the integral of g. Again, it should make sense because if f is higher, then it's accumulating more space underneath it than what would be accumulated under g. Is that average height? No, not average. If f of x needs to be strictly greater than or equal to g the whole time. If we were thinking about average, then we might allow f to dip underneath g for a brief second, but I'm not ready to say that that is always true yet. this domination property is simply if f is always greater or equal to g, no holds barred. I don't know why I said no holds barred. Anyway. All right, let's finish up with just last few examples. Let's just get comfortable with how integrals work and their properties. I don't want to spend too much time on these because I'd rather you guys look at the first few on your own. So take a look at this integral. We've got the integral from -1 to 1 of what function? Absolute value of x dx. Can someone tell me what this graph will look like of the function then? It's going to be a v. Will this v be moved left or right at all? Will it be moved up or down at all? Will it be flipped at all? All right, so let's just draw in a v. Okay, there we go. This is the absolute value of x. Now, where are we accumulating area? -1 to 1. So we're going from -1 over to 1. Now, you have a couple options that you could do this with. Notice that this shape geometrically is what? Can someone describe it for us? It's two triangles, or you could think of it as a square. However, do you really need to compute the area of two triangles? We could do 1 and then multiply by 2, or don't divide it, or however you want to think of it, because absolute value is symmetric. So the area from -1 to 0 should be the same as the area, the accumulation from 0 to 1. Regardless, I'm going to do it as two separate triangles. So this integral would be equal to, what's the base length of the first triangle? 1. The height of the first triangle is also 1, and then it's times a half. That's the first triangle. And then, as we observed before, the second triangle isn't going to be any different. The base length is still 1, the height is still 1, and then times 1/2. So what does this integral end up being? It ends up being equal to 1. 1/2 plus 1/2. Up. Hang in. That's why people had confused looks on their faces. Okay, there we go. Thank you. Whoops. Okay, all better? All right, here we go. 1/2 plus 1/2 is 1. What if this integral were from 1 to -1 instead? How would that change our answer? If the integral were listed as 1 to -1 instead, we would be moving and accumulating area backwards. So this would be -1 instead of 1. All right. I want you guys to give this a shot. See if you can, at the very least, draw the function that this is asking you about, and then sketch or shade in the region that it's asking you about. Remember, your graph doesn't need to be exact either. As long as you have the ability to figure out the dimensions of the shapes in the graph, you should be okay. So while you guys are finishing, let me just pick up here. What is this shape? Or what is the shape of the graph going to end up being? it'll be two triangles. The graph, when we graph, it'll be a line, is what I'm trying to get at, though. The line has a y-intercept of what? 0. And a slope of 3. So I'm just going to draw some random that was all right. This has a y-intercept of 0. Okay? All right.
There we go.
I'm going to draw in a random line, and I'm going from -1 all the way out to 4. And we're dealing then with two triangles. One triangle will be counted as what kind of area? Negative area. And the other triangle will be counted as positive area. So this is the positive triangle right here, because we're going from 0 to 4, and this is the negative triangle. Because it's below the x-axis, we're going from -1 to 0. All right. What's the area of that first negative triangle? So it'd be 1. What's that? 1 times 3 divided by 2, right? So 1. What I like to do is in the drawing, I like to label my dimensions. The width of that triangle is 1. This dimension of the triangle is like 3. I know what you're thinking. Why am I not doing that as -3? I like to find the area of this as if I was in a geometry class. So 1 times 3 divided by 2 is equal to what? 1.5. And then, because I know it's negative, I just write -1.5 up top. Okay. What's this dimension on the positive triangle? 4. And what's the height of the positive triangle? 12. So this would end up being 4 times 12 divided by 2, 24?
Yeah.
Okay. So this integral ends up being 22.5.
How'd you get 12?
It's 4 times the slope. Yeah. So you could just imagine like you're plugging in the x value into the function to get the height. All right. Last thing, and this is the quickest. So in the last little part of your notes here, can I have you guys write down these 3 integrals? And I just want to ask you a few questions about them. I know that I'm running a little bit long here, but these are simultaneously the easiest and the most confusing sometimes to people. So we have the integral from 3 to 7 of f of x dx. I'm telling you that that's 13. The integral from 3 to 7 of g of x is 5. And the integral from 7 to 9 of f of x is -4. So the first thing I want to ask you is this. You guys agree, Scott? 18? Yep. This would be 18. You might also see this written like this. 3 to 7 of f of x plus g of x dx. It's another way that you might see it. Because remember, we can split up integrals across a plus.
Wait, what is the 3x? Oh,
That's the lower bound of the integral on top. It's not f of x cubed. What about this example? Four? You guys agree with Hannah and Jack? Why is it 4? We're accumulating backwards, so we're making negative the area that it was before. So this is positive 4. And last, Can someone tell me what that integral is equal to? Am I asking a trick question right now? Yes. The answer should be no. No one can tell me what that integral is equal to because, well, we don't know, quite frankly. If we knew what f of x and g of x were, maybe we could compute it. But as of right now, we're not given enough information. So this is a big no. You can't figure out what this is. At least not from what I had given. Okay. That's all I've got for definite integrals. Tomorrow you guys will have pretty much the whole time to work on them. I would highly recommend taking a look at the first few routines. I know that it's been a long lesson, but take a look. I want you to get comfortable with definite integrals as soon as possible. All right, thanks.
This next out.